So when the consumer chooses an optimal bundle, so recall what our models look like. The consumer faces some prices and some income, and then chooses the object in the budget set, in the set of affordable bundles, which maximizes her utility. And we called that bundle, or that set of bundles, the Walrasian demand. The Walrasian demand was the set of bundles which maximized the consumer's utility function subject to the budget constraint. Now, a natural question is how much does this consumer like this state of affairs? Is she well off or poor off or whatever? I don't know what the opposite of well off is. Getting hurt. And so how do we do that? We think about the indirect utility function. So the indirect utility function says, what is the utility of facing a set of prices and an income? How well off am I under the set of prices and an income when I'm behaving optimally? So that's just the utility of the Walrasian demand. So once again, we should probably just try to parse this notation, this mathematical notation. So V is the standard notation for indirect utility function. It goes from Rn++ cross R plus to R. So Rn++ is the set of n prices, positive prices. Then R plus is the income, and that has to go into some number, which is a real number, which is the utility associated with facing the price vector P and the income I. And it's just going to be defined as U of X star. Now this is a slight abuse of notation because remember X star is actually a set. It's possibly many different bundles that all are optimal, but since they're all optimal, they all yield the same utility, right? If one thing in X star was better than another thing in X star, the other thing couldn't possibly be optimal because there was something better than it. So everything in X star definitionally provides you with the same utility, and therefore, despite this being slightly bad notation or naughty notation or something, V is well defined. So V is the utility of any of the elements of X star. So now that we have this idea in our tool house, in our tool shed or toolbox or whatever, we can easily answer questions like, is the consumer better off when prices are Pi or when prices are P prime I prime? So would the consumer prefer to be in the regime, I don't know why they're called regimes, the regime Pi or the regime P prime I prime? You can think about this as, there's two different jobs that she could take. One is in a city where prices are P and her income will be I. The other is in a different city where her prices will be P prime and her income will be I prime. All this is really asking is V of Pi greater than or less than or equal to V of P prime I prime, right? V of Pi is how much do I like having prices P and income I. V of P prime I prime is how much do I like having prices P prime and income I prime. And so the relation between these two numbers tells me if the consumer would prefer one regime over the other. So let's just work through a quick example. We had this utility function ln x plus ln y, and we had the prices P1, P was 1, 2. So under 1, 2, when x costs 1 and p costs 2, remember that the Walrasian demand was I over 2 units of x and I over 4 units of y. And therefore, the indirect utility is, we just plug that back into the utility function. So log of I over 2 plus log of I over 4. If you remember your logarithms, if you're adding logarithms, you're multiplying the interiors, so you get the log of I squared over 8. So under this particular regime where the prices are 1 and 2, the indirect utility of the consumer is I squared over 8. The log of I squared over 8, right? So this last line is the indirect utility of this particular regime under P and I. Now let's say the income is constant, but now the prices have changed to 3 halves, 3 halves. So notice that 3 halves, 3 halves adds up to the same thing. So the total price of buying 1 unit of X and 1 unit of Y has remained the same. But instead of it being concentrated that Y is more expensive and X is less expensive, now they're the same cost. So does the consumer prefer this, making Y cheaper and making X more expensive, or would she prefer that X was cheap and Y was expensive? So under P prime, we can rewrite our Lagrangian, and that's just u of xy minus the lambda times our budget constraint. We have the same kinds of first order conditions that we've been working with the whole time. We divide x by y, we get y over x, which is the marginal rate of substitution, is equal to 2/3 over 2/3, which is 1, which means that y over x is equal to 1, means x is equal to y. Of course, you could probably have anticipated that they're totally symmetric, so you're probably going to spend the same amount of money on both of them. And that means that x star equals y star equals I over 3. Right? You plug back into x equals y into your budget constraint, you get x star equals y star equals I over 3. You spend equal amounts on the two goods, and you get the same amount of both of them. Now, the indirect utility associated with x star and y star equaling I over 3 is log of I over 3 plus log of I over 3, which is equal to the log of I squared over 9. And I squared over 9 is less than I squared over 8. So, and the log is a monotone function. So the consumer prefers the unequal prices. The consumer prefers the price regime 1, 2 over the price regime 3 halves, 3 halves. And look at how easy it is to answer that question, right? At first, it might sound like a kind of daunting question, which was, does the consumer, with this abstract utility function and these two different prices, which one do they like better? And we can solve it in 2 minutes, right? It's totally simple now. And these are the kinds of things that's really harnessing the power of this type of thinking. So yeah, it's a hopefully you feel like this is kind of cool and you've done something by now in this class, hopefully. So we can actually make this a little more general. Let's just say you have px is the price of x and py is the price of y. We don't need to know what those things are. They could be any px and py. You have the same kind of Lagrangian, the same kind of first order conditions. You divide x by y, and you get that y over x equals px over py, which is the same as saying y equals x px over py. You plug that back into the budget constraint, and you get 2x px equals I. Let me go a little slower. I can show you how that works. So you have p. So you have y over x equals px over py, and you multiply both sides by x, so you get you take the x over here and you get an x here, right? Now we're going to plug this into the budget constraint so we have px x plus py y equals I. So we're going to plug this y in for that, and we get px x plus py px py x, and the py's cancel, and so you get pxx plus pxx equals I, or 2pxx equals I. So that means that x star is equal to I divided by, right? So then we just can divide both sides of that last equation by 2px, and we get that x star is equal to 1I over 2px. Plug that back into our definition of y, and we get that y star is 1I over 2py. And that means that our indirect utility is the log of I over 2px plus I over 2py, which is equal to the log of I squared over 4pxpy. And now we've gone from solving one individual problem that dealt with one individual set of prices, one price vector, to looking at what is the utility of this consumer. How much does a consumer like for any vector of prices? You could just go ahead and plug in any vector of prices in here and know immediately if this consumer would prefer that or another one, right? So you give me any two vectors of px and py, and I just plug it into I squared 4 over px py. I just look, is it bigger or smaller? And I know immediately if this consumer prefers one regime to another. This is an extremely powerful way of thinking about these kinds of problems because it synthesizes all the different kinds of things into one very simple to parse equation.